Okay, so for today we are going to cover the second last chapter. Okay, so if you look at the academic calendar, okay, so we have 4 more weeks to go before the end of the semester. Okay, I think the semester will end on the, if I'm not mistaken, on the 24th of June. Okay, whereby the following weeks after that will be the what we call the exam weeks. Okay, of course, most subjects during this COVID-19 teaching period is done during the assessment is done using your tests, online tests, okay, and also assignments. Okay, so but some subjects do have exams or tests during the exam break or the exam week. So I think we have more than enough time. Actually, we may in fact actually finish earlier than the stipulated schedule. Okay, so this I think we can finish the 2 sample hypothesis test maximum by end of next week. Okay, because I think once we have good understanding on the 1 sample hypothesis testing, the 2 sample test will be pretty much similar to what you have done in the 1 sample hypothesis testing. Okay, so let's get on with the lecture. Okay, so what we have done in the 1 sample test before is basically looking at the word 1 sample means we are only testing hypothesis based on 1 sample that we collect. Okay, a sample of 20, a sample of 30 individuals. Okay, so based on the exercise that you submitted recently, okay, so we're just going to extend that concept of hypothesis testing, okay, whereby the 5 steps that you have carried out with the 1 sample test will still be applied here. Okay, so the only difference is that this time around we have 2 sample, okay, but the nature of the test still follows the 2 distribution, whether you are going to use Z distribution, okay, when the sigma is derived from the population, or using the T distribution when the sigma is unknown. You can see from these items here, unknown standard deviation. So this will clearly using the T distributions. Okay, and then we also have the Z distribution. Okay, so similar to the previous chapter as well, we have the proportions concept as well. Okay, but again, since this is part of the syllabus, we are going through this. We will go through this concept as well, but in terms of the focus of the discussions of the exercise and also your assignments later on, okay, we'll be focusing mainly on the T distributions when sigma is unknown, and some will be dealing on the Z distribution, okay, when the sigma is derived from the population. Okay, so and continuation from this, okay, we will go for the final chapter on the ANOVA. Okay, some of the concept that we learn on the 2 sample test will be applied in the final chapter. Okay, so let's get started. Okay, so what's the difference between 1 sample and 2 sample? So some of the topics or some of the concepts, okay, whereby you can apply a 2 sample test. For example, you want to compare between gender, okay, male and female in terms of the sales, okay, the mean between different time, okay, day and afternoon. So as long as you are comparing 2 different set of samples, okay, whether they completely different, for example, male and female. Okay, for example, in our UUM, okay, in the statistics subjects, we have different groups, okay, group A, group B, group C. Of course, there are more than 2 groups. But let's say we want, I want to compare just the performance between group A and group B. So as long as it only involves 2 samples, then we can apply what we learned in this chapter. Okay? But if you want to compare more than 2 populations, for example, 3 populations, 4 populations, group A, group B, group C, group D, and group E, for example. So let's say there are 5, I think there are 5 groups of statistics this semester. So if I want to test the performance of each of the, I mean, if I want to see whether there are differences in the performance of students for all the 5 groups, that for students taking the statistics this semester, then the best method that we're gonna apply is the ANOVA, which we will learn in the next chapter. Okay, so the two sample hypothesis testing is only meant for two sample alone. Okay, more than two, you need to use ANOVA. Okay, so what you see here, okay, so sometimes in the research world, okay, the two sample might be appropriate. Okay, especially if you're only comparing two, lah. Okay, A and B, male and female. Okay, so those kind of, for example, this COVID-19 vaccine. So of course there are more than two versions. Okay, AstraZeneca, the Sinovac, Pfizer, okay, the Johnson and Johnson from UK. So there are different type of vaccine available. So if you want to test the efficacy, okay, the effectiveness of the vaccine, okay, in preventing the spread of COVID-19 virus, okay, so then that will require the use of ANOVA approach, for example. But if you are only comparing, let's say, the performance or the effectiveness of Pfizer versus Sinovac, then you can apply the two population hypothesis testing. Okay, so these are just example. Of course, in the real world, okay, there are more than, I mean, you can find different instances for examples that can be related to the two population hypothesis testing. So how do we perform this? So if you compare from the previous chapter, okay, one sample test. Okay, so let me open the one sample test so that you can see the difference in terms of the formula, okay, in the calculation of the okay, so either you are using Z or T, so the formula will be X bar, the mean of the sample, minus the population mean, okay, divided by the standard error. Okay, and if you recall, your null and your alternate hypothesis is only in terms of mu equals to something, okay, and then H1 mu not equal to, or it can be mu more than, okay, or mu less than for H1. So it's always in terms of mu and followed by a value, okay, because we are only testing for one sample. So in the one sample hypothesis, it's always start with mu followed by a certain value, whether it's not equal to, more than, or less than. Okay, so but unlike the one sample test, okay, in terms of the calculation, whether you are using Z or T, okay, so you don't, if you look at the one sample, okay, in terms of the formula, X bar minus the mean value, okay, but for two sample, because you are comparing between two population, so you must take the difference between the two sample mean, X bar from the sample 1 minus X bar from the sample number 2. Okay, and then for the standard error, you need to combine between two of the populations. Okay, so first part, if you look at the title here, comparing two population, equal variance. Okay, so equal variance means we assume that the variance between the two populations are equal. So if that is the assumption, then this will be the appropriate formula. Okay, so the mean is the numerator, X bar 1 minus X bar 2. Okay, so you are given the two means, the two mean value from the two sample. So you need to take the difference between the two. Okay, so X bar 1 minus X bar 2. So how do you know which one to deduct first? Okay, can you also do the other way around, X bar 2 minus X bar 1? Yes and not. Okay, it depends on how you write your H1 and also your H0. Okay, so I will explain that later. So for example, the difference between group A and group B performance. So if I want to see the difference between group A and group B, okay, so X bar 1 minus X bar 2, okay, can it be the same also if I put X bar A minus X bar B, or X bar B minus X bar A? So the other way around, is it correct just to simply choose whichever order of the difference? Okay, so that one, you need to see how you construct your null and your alternate hypothesis. Okay, so first, if you look at this simple example here, Okay, so if you look at this information, so the company wants to see if the difference in the checkout time. So if you go to any grocery store nowadays, okay, whether a big one or a smaller size grocery store, okay, especially the big macro style like Tesco, okay, shops, okay, or you can see that most of them are using the barcode system, okay. So they want to see if the method between the old method, or I mean like the standard method versus the new scan method, okay, is longer. Okay, they want to know if the standard checkout time is longer than the new scan. Okay, so the time taken from the standard, I believe standard is the older method, okay, is longer, meaning it takes longer time for the customers to check out, okay, or to finish scanning their items at the counter. Okay, so she gathered the following sample information, okay, and then you want to test. So the keyword here is longer. If the mean from the standard is longer than the mean from the use scan, okay, so you are given the population standard deviation. So as long as the sigma from population is given, so you are required to use the Z distribution. Okay, so if you recall from this previous formula here, x bar 1 minus x bar 2. So which one is 1, which one is 2 here? Is it the use scan or is it the standard scan should be number 1? Okay, so let's see how the H1 and H0 is constructed. Okay, because the objective of the study want to evaluate whether the time taken from the standard, okay, so whenever you construct your H1, okay, unlike in the one sample test, okay, if you look at the one sample test, the way you construct your H1 and your H0, you just put mu, okay, there is no subscript in the mu because there is no, because you're only referring to that particular sample. Okay, there is no mu subscript 1 or mu subscript x. Okay, but in the two sample hypothesis testing, it is compulsory for you to denote your both of the population mean with a subscript. Okay, so that you are, so that we know which mean is that referring to. Okay, so the notation or the subscript s, I think, is understood, refers to the standard. Okay, U refers to the use scan method. So you want to test, okay, because the objective of the study is to determine whether the time taken of the standard, the mean is from the standard is longer. Longer means it should be higher than. Okay, so if you, this is the way how you construct your H1. So in other words, mu s appear first, followed by mu u. So if you look at the formula from the previous slide just now, one should be the one that whatever appear in the first notation in your H1 or even your H0, the order of the appearance in your null hypothesis and also your alternate hypothesis will be, so whatever appear here first will be the one value x bar 1. Okay, this one should be the x bar 2. So that's how you decide which one to deduct first. Okay, x bar 1 minus x bar 2. So in this case, x bar 1 will be the standard scan method, the mean value of the standard. X bar 2 will be the mean from the use scan method. Okay, so once you have constructed your H1 correctly, so of course, start by finishing up with your H0, because this is more than, similar to the previous chapter, the complement or the opposite sign will be the less or equals to. So in this part, I think there is no difference in terms of the sign. It is just that here, because we are doing two sample tests, so unlike in the one sample whereby the mean is followed by a value, okay, but in a two sample hypothesis testing, there is no value that you need to put in here. Okay, but what is the point of what is important is which one you are comparing, whether it's more than, less than, or not equal to. Okay, because the keyword is longer than, so we choose the more than sign. Okay, so step number 2, the alpha is given as 1%. So the test given, I mean the test that you need to use is using the Z distribution because sigma is given. And finally, step number 4 will be the decision rule. So I think, and in this stage, it will be the same as in the one sample test. If you are doing one sample test, one tail, the sign of your H1 is more than, so automatically that will represent a one tail test on the right. So because it's 1%, 0.01, so this will be 0.01. This remaining part will be 0.49. When you check your Z table, 0.49, the value closest to that will be 2.33. So in this part, I think there is no difference between one sample or two sample when it comes to using Z distribution. But when it comes to using the T distribution, there will be some difference, because now you are comparing two population, and the degrees of freedom, DF, will be different as well. But for the Z distribution, whether it's one sample or two sample, it doesn't matter. The way you read the Z table remains the same. As long as if you are using one tail test, okay, in this case, it will be one tail on the right. So 1% means the area on the right will be 0.01. So the remaining here will be 0.49. If I change the sign to not equal to, meaning a two-tail test, so 1% you need to divide by 2. So it means the area here is of 0.01 now becomes 0.005. So if this is 0.005, if it is a two-tail test, so this remaining area will be 0.495. So you refer to 0.495 in the Z table. So I think you will get the value to be 2.58. Okay, so the approach of determining the critical value, okay, the critical value here, for Z distribution is exactly the same, whether one sample hypothesis testing or two sample hypothesis testing. Okay, do not get confused between the word two sample and versus the word two tail. Okay, so two tail means you are looking at two sides of the tail in the distribution. Two tail means the sign of your H1 will be not equal to. Okay, but two sample hypothesis testing, you are comparing between two different population, male and female. Okay, so two sample versus two tail. So maybe if you are clear on this, I think should be no problem. Okay, so here we are doing a one tail test on a two population, on a two sample hypothesis testing. So here we have determined that our critical value will be 2.33. Okay, and then you draw your area of rejection, okay, your normal distribution diagram, and highlight the area of rejection, indicating what is the line for the critical value line. Okay, so here I think there is no difference. And then finally, you plug in into the value and then do your conclusion. So x bar s minus x bar mu u. Okay, you recall just now, because your H1 is constructed as mu s bigger than mu u. So when you want to do the calculation, it will be x bar s minus x bar u. So that's what you see here, x bar s minus x bar u. The order how it appeared in your H1 must be followed, must be follow suit in your calculation as well. And the rest is just plug in. Okay, sigma s, sigma square s divide by n. Okay, so this information is given, so you just simply include them in your plug in into the equation, and you should derive the final answer here to be 3.13. Okay, and then again the three parts conclusion, part 1, part 2, and part 3. Okay, first part is whether the value is inside or outside the area of rejection. Okay, second, whether you reject or do not reject. Third, the meaning of your conclusion. Okay, of course, if you look at this conclusion here, it is much shorter than what you used to see. Okay, for me, stick to the one that you normally do in the chapter number 1, chapter 9, chapter 8 before, on the one sample test. Okay, we conclude that, okay, the mean of something is not, the mean is not equal to, the mean is not greater than, or the mean is less than. So in your hypothesis testing, okay, our H1 is what? Mu s or mu standard is longer than the mean of U scan. So in our case, we reject the null hypothesis, correct? Because 3.13, okay, 3.13 is bigger than the critical value, so we reject. So because we reject the null hypothesis, our conclusion should be the mean of the standard time, or the time, the mean checkout time from the using the standard scan method is longer than the time taken in the use scan method. Okay, so you can answer that way. So whatever that you answer, always go back to your H1. If you reject H0, means you can support the statement. If you do not reject H0, means you cannot support the statement. So either way, you need to refer back to chapter 8 before, okay, whether you include the word not or you remove the word not in your statement number 3. Okay, here because we reject H0, okay, so we have evidence that mean S is bigger than or is longer than the mean of U. Okay, if you do not reject, you need to add the word not. The mean S is not longer than the mean of U. Okay, so that is also another way to answer. Okay, so as long as you but I think at this stage, once you have done a number of exercise on the hypothesis testing, okay, this also is a correct method to explain your conclusion. Okay, the use scan method is faster. Use scan method faster. Why? Because when you reject the null hypothesis, what you are saying, the standard scan is longer. So the reverse will be true lah. Meaning if that is longer, the standard scan is longer, mean that use scan is faster lah. So either way is correct. Okay, but if you are unsure, okay, always go back to the standard way of answering, which I think the easiest or the safest way is to write down based on your H1. What is your H1? If you reject, means you can support H1. Okay, if you cannot reject, means you just add the word not in your conclusion for the third sentence. Okay, so I think I have discussed this in detail in the previous chapter. So go back to the video if you have forgotten how to write down your the third part of your conclusion. Okay, because explaining or writing down the correct conclusion will be one of the important component, okay, in doing hypothesis testing. And your assignment will be evaluated based on that as well. The way you correctly written, okay, correctly write your conclusion, okay, for the hypothesis testing. So this is for when sigma is given, whereby we are using the Z test. Okay, so that is the first part. Okay, on the proportion, okay, I will skip this part first, okay, on the proportion thing, okay, because as I mentioned just now, the focus will be more on the t-test. The t-test followed by the z-test that we just covered just now. On the proportion, even though it is part of the syllabus, okay, but in terms of the application in the real world, the one that is more relevant will be using the t-test when sigma is unknown. Okay. So the first part, okay, on the t-test will be comparing the mean with equal but unknown population standard deviation. Okay, so this is what we call the pool t-test. Okay, if I scroll through the slides, okay, so this is the pool t-test, and then okay, so beside the pool t-test, we also have what we call the dependent and independent sample. Okay, so this is also using t-test as well. Okay, for what we call paired t-test. Okay, so in the t-test family, I mean in the t-test in the two sample hypothesis testing, when it comes to using t-test, there are two parts in the syllabus. One is what we call the pool t-test. The second part will be the dependent versus independent sample. Okay, so this is also using t-test. Okay, so I want to spend more time on discussing this. Okay, so I think for today's lecture, okay, we will cover only until the pool t-test. Okay, on next Monday we will cover on the dependent versus independent sample using t-test as well. And hopefully by sometime by before end of next week, we can finish up the syllabus on a bit discussion on the proportion, and I will give you some example and some exercise, and also we'll be handing out to you the assignment questions, okay, that you need to complete. Okay. So, but the submission time for your assignment, okay, I will update that one later. Okay, I need to discuss with the other lecturers as well. How do we decide to set the time, whether you can submit together with assignment number 2 during the exam week, okay, or you need to submit earlier. Okay, so that one will be updated later. Okay, so let's start on the pool t-test first. So what does it mean by pool t-test? Okay, so first and foremost, of course, the condition is unknown standard deviation. Unknown population, sigma, means the sigma is derived from the sample. Okay, so this condition here, less than 30, okay, I think one part from the one sample test last week, I asked you to remove this condition, correct? Okay, because I think as far as your syllabus is concerned, as long as you are using the sigma from the sample, directly we are going to use t-test, regardless whether the sample size is more or less than 30. Okay, so I think on this part here, so let me delete that part. I'm not saying that that part is wrong, okay, but just to make your life simple to understand, which test are you going to use, Z or T? So as long as sigma is unknown, we are going to use the t-test. Okay, when the sigma is known, meaning sigma of the population is known, we are going to use the Z test. Okay, that's it. That is our rule of thumb. Okay, and also the assumption is that it must follow standard deviation. Okay, and the sample must be taken from independent population. What it means by independent? Between sample 1 and sample 2, they are not from the same population. For example, male and female. Okay, you cannot take the male and female from the same population. Okay, it must be taken from a different set of population. Okay, so let's see first in terms of the formula. Okay, of course, even if you were to answer this type of questions in your exam, in actual pen and paper exam, if you were to come to UAM and do the normal exam style, okay, all of the formulas will be provided to you in your exam booklet. So you do not need actually to memorize this formula, even in the real exam. Okay, but what you need to know is which formula to apply depending on the condition or the situation of the question. So of course, you apply the t-test when the sigma is unknown. Okay, you apply the Z test that we just discussed just now, okay, when the sigma is derived from the population. So the formula, that's what we mentioned just now, is what we call the pool t-test. What does it mean by pool? Meaning you need to combine the value of the standard error. Okay, pool the sample standard deviation. So meaning that this formula is what we call the pool t-test. Okay, so the formula for S squared P stands for pool. Okay, sample size number 1 minus 1 multiplied by the variance of that sample. Okay, S1 squared means the variance value or standard deviation squared. Okay, plus N2 minus 1 multiplied by the variance of sample number 2 divided by the combined value of the two samples minus 2. Okay, and then followed by the t-test as well. So again, x bar 1 minus x bar 2. Okay, which one is 1, which one is 2 is the same as what we did before, depending how it appears in your H1. Okay, whichever mean that appear first, that will be your x bar 1. Okay, the one that appears on the second, on the next side, on the second value will be your x bar number 2. Okay, so once you have calculated the S squared pool, okay, so plug in into the denominator here, okay, and okay, so S squared P, okay, multiply by the sum of 1 over N1 plus 1 over N2, okay, the product of this, then you need to take the standard, you need to take the square root of that, okay. So that is, okay, if you look at this part here, N1 plus N2 minus 2. If you recall from the previous chapter, okay, in the one sample hypothesis testing, okay, whenever you want to use the T table, Okay, if you recall, whenever you want to use the T table, one of the characteristics of the T table is what we call the degrees of freedom, correct? Okay, if yours, let's say in the one sample test, if your sample is 20, then your DF will be 19, correct? Meaning you take the form, you use the formula n minus 1. This is only for one sample test. If your sample size given as 20, you need to refer to column that refers to 19. Okay, so that is what you did in the one sample test. But for two sample tests, okay, because you have two sample, so your degrees of freedom now will be N1 plus N2 minus 2. So let's say N1 is 10, N2 is let's say 12. So the sum of both will be 22. So 22 minus 2, you will get 20. So in the T table, 20 will be your degrees of freedom. So the formula that you see here, N1 plus N2 minus 2, is also equivalent to your degrees of freedom, DF, that you need to refer to the T table later on when you want to determine what is the critical value. Okay, that will be in your step number 4. Okay, so in chapter number 9 previously, okay, your DF will be based on n minus 1 because you are only using one sample. But for two sample, you need to refer to this formula here, n1 plus n2 minus 2. Okay, and finally, okay, and finally, okay, let's see one example, okay, from this slide. Okay, so you have this one company, okay, manufacturing two different type of lawnmower, okay, pemotong apa, ya, rumput, okay. So you have the time taken to, okay, 5 employees were time using the these two machines, okay, okay, and then 5 employees using this machine, okay, wellies, and the other machine, there are 6 employees, okay, using this machine. So the time taken is given here. Is there a difference? Okay, so the keyword here, is there a difference? So difference, as what we did before in the previous chapter, the notation for H1 will be not equal to. Okay? Is there a difference between the time between the two methods? Okay, so when it comes to is there a difference? Okay, so meaning that you need to take the difference between the two mean values of Wellis and also Atkins, okay, in this case. So in this example here, okay, so okay, if you look at the slide, okay, they only use the subscript 1 and 2, okay, but I think one of the weakness, okay, from this part here, how they design the H1 and your H0, is that you do not know what is 1 and 2. So in your case, okay, if you were to answer, let's say something like this, you need to show what is, you need to use the appropriate subscript as what you saw in the previous example on the Z testing, okay, on the standard scan and also the U scan, okay. So instead of using just one and 2, okay, you can use the symbol U and S, okay. So here, okay, if you look at the calculation, okay, Wellis, okay. So if you look at this information here, Wellis and Atkin. So in terms of whenever you want to test a different, actually it doesn't matter whether Wellis minus Atkins or Atkins minus Wellis. But again, it's how you write down your H1. Because when it comes to difference, okay, compared to longer or bigger than or smaller than, that one must be correctly, you must put the notation or the sequence in your H1 correctly. But if you are testing a difference, so it doesn't matter whether you can put, let's say student number 1 put U1 not equal to number 2. Student number 2, she put, let's say the student put, instead of U1, she put U2 not equals to U1. So if that is the way, it is also correct, okay, because um, Okay, if that is the because if you put u2 not equals to mu1, let's say 1 is Wallis, 2 is Atkins. So if student number 1 put mu1 not equal to number 2, then that will be Wallis minus Atkins. If another student put mu2 not equal to mu1, means that 2 is referring to Atkins, then she is referring to Atkins not equal to Wallis. So in the calculation, it will be Atkins minus Wallis, not Wallis minus Atkins. Okay, because whenever you do a two-tail test, a not equal to sign, you are going to test on the both sides of the tail, left and right. So either way, you are going to come out with the correct conclusion as well. Okay, of course, the answer will be the opposite sign. Let's say if you put Wallis minus Atkins, you may get a positive value. Okay, but if you put Atkins minus Wallis, the same answer, let's say Wallis minus Atkins, you get positive 4. But if you put Atkins minus Wallis, you may get negative 4 as the answer, just for example. So, but because the nature of a two-tail test not equal to, you are looking at the two sides of the tail, left or right side in your distribution. So even though the answer will be the opposite sign, depending on how you write your H1, but the conclusion will still be the same, because if you get plus 4, meaning you are looking at the right side of the tail. But if you get negative 4, you are looking at the negative side of the tail. Either way, the conclusion will be the same thing, will be you are arriving at the same conclusion. Okay, so for not equal to sign, okay, for a two-tail test, doesn't matter. Okay, it can be, so even though one student define Wallis as the first sample, okay, Atkins as the second sample, or another student define Atkins as the first sample, Wallis as the second sample. So either way, both are still correct when it comes to arriving at the conclusion. So I think in this example, the book defined Wallis as sample number 1. Okay, so if you look at the calculations later on in the next few slides. Okay, so what I will do is, instead of using 1, okay, the best will be to put here, let's say, use W, and 2 is Atkins. Okay, the same thing here, it will be W. This will be Atkins. So W stands for Wallis method. A stands for Atkins. So you are testing, is there a difference between the mean of Wallis and not equal to the mean time of the Atkins? So if I decide that Wallis appear first in the notation in my H1, so in the calculations later on, okay, in this formula here, X bar 1 will be referring to Wallis, because in my H1, Wallis appear first in this part here. Secondly, it followed by Atkins. So X bar 1 will be Wallis, X bar 2 will be Atkins. So I hope you are clear on that. But if another student, let's say, put the other way around, mu A not equal to mu W, the other way around. So in the calculation, it will be, okay, X bar 1 will be Atkins minus Wallis. Okay, because you define Atkins first, mu A not equal to mu W. So it will be Atkins minus Wallis. Okay, so you must be consistent on how you write down your answer later on. Okay, if the formula, if the Wallis appear first, then it will be Wallis minus Atkins. If Atkins not equal to Wallis, it will be Atkins minus Wallis. Okay, so that is the process of writing, constructing your H1 and also your H0. Okay, so step number 2, you are given the alpha 10%, okay, not 1%. Okay, here I think they are using a bigger alpha, 10%. Okay, and then the test, we are going to use the pool t-test. Okay, so just add the word pool here. Okay, even though you don't put the word pool, you just mention t-test, it still be correct lah. Okay, because t-test okay, is referring to the t distribution. Okay, here again, because you are doing a two-tail test, so there will be 2 critical values. One is the positive value, and the second one will be the negative value. So again, as usual, you need to plug in what is the positive value. Here is 1.833, and here will be negative 1.833. Okay, so how do you get 1.833? If you refer to the T table, okay, so if you recall, okay, how many samples that we have here in this question? Okay, we have 5 samples from Wellis, 6 samples from Atkins. So meaning 5 plus 6, you have 11. Okay, 5 plus 6, 11. So if you remember the formula, N1 plus N2 minus 2. 5 plus 6, 11 minus 2 equals to 9. So you are going to use 9 in your degrees of freedom. So here in the T table, okay, you are going to use 9. So 9 will be the degrees of freedom. Okay, you obtain 9 by N1 plus N2 minus 2. 5 plus 6 minus 2. And then 10%, okay, not 1%. And remember, okay, in your T table also, you have the 1-tail test or the 2-tail test. So you need to refer to the 2-tail test part here, not the 1-tail test. Okay, because if you're referring to 1-tail test 1%, it will be this column here. So you, instead of using 1.833, you might be using 1.383, which is wrong, nah? Okay, because here is 10%, but under 1-tail test. But because the sign of your equality in your H1 you put not equal to sign because you want to test the difference. Is there any difference? So difference means you are doing a 2-tail test. 2-tail test, and then your DF you decide to be 9. You obtain by N1 plus N2 minus 2. So 9 under 2-tail test, 10%, it will be 1.833. Okay, so that's how you obtain this value of 1.833 on the left side and also on the right side of the distribution. So remember, whenever you are doing a 2-tail test, your critical value, your decision rule, okay, in step number 4 must also followed by 2 different values, one on the positive, one on the negative, more than a positive value and less than a negative value of the same value. Okay. And finally, the calculation. Okay, so here it will be similar to what you did in the exercise 2 days ago, okay, or yesterday when you submitted the exercise. Okay, because the data is raw, meaning you need to calculate what is the mean value, what is the sample standard deviation value. Okay, so I think in terms of deriving, for example, for Wellis X1, you for the Wellis method, you get the mean to be 4, and the sample standard deviation you get 2.9155. The sample mean for Atkins is 5. Sample standard deviation is 2.0976. So in getting these two separate values, 4 and 2.9 and 5 and 2.09, I think should be no problem at this stage. Okay, because if you know how to do it for the previous exercise, okay, calculating the mean, especially the sample standard deviation. Okay, so the same process here. So the only thing that you need to do is first you need to get what is the mean and the sample standard deviation before you can calculate the pool standard deviation. Just follow the formula in the book, okay, and then I think should be fine lah. So if you look at this solutions here, okay, N1 minus 1 multiplied by the variance of sample number 1, okay, until the end. So you can see how it is being applied here, simple and straightforward. So the first one will be N minus 1, 5 minus 1. Okay, for Wellis, there are 5 samples multiplied by the 2.9155 squared, followed by sample number 2. There are 6 samples in Atkins minus 1. Okay, multiplied by the variance, divide by 5 plus 6 minus 2. So this is just to get the pool variance or pool S squared P. Okay, so you get 6.2222. So that will be the pool standard deviation. Okay, and then finally, to determine the value of T, or step number 5, calculate the T value and make a decision. So here is also the same, X bar 1 minus X bar 2. So remember, X bar 1 refers to the Wellis value. Why Wellis? Because that's how you write down your H1. You put H1, Wellis, not equal, the mean of Wellis, not equals to the mean of Atkins. So in the calculation part, it must be also followed by the mean of sample mean of Wellis minus the sample mean of Atkins. So 4 minus 5 divided by the pool variance, the pool standard deviation, okay, and you get negative 0.662. Okay, if you look at this number here, okay, negative 0.662, you get this number because you put Wallis minus Atkins. If another student were to put the other way around, means that in the H1, okay, in the H1, the student write the mean mu of, instead of Wallis, she put Atkins, okay, mu Atkins not equals to the mu of Wallis. So in the calculation, it will be the other way around. Instead of 4 minus 5, it will be 5 minus 4. So, but the bottom part will be the same, okay, because this is just the pool variance. Okay, but instead of getting negative 0.662, if the student write down the other way around, she will get positive 0.662. So is this right or wrong? Both are still correct, because if you get the one like in the slide, okay, which is negative 0.662, you are going to compare on the left side of the tail. Okay, but if you get positive 0.662, you are going to compare on the right side of the tail. Okay, either way, the conclusion will still be the same. Okay, but remember, if you put 5 minus 4, this must be also correctly represented in your H1. Okay, you cannot put in your H1 values not equal to Atkins, but in step number 5, you put the other calculation, meaning you put Wallis Atkins minus Wallis. So this is wrong. Okay, so if you write your H1 Atkins not equal to Wallis, so it would be Atkins minus Wallis as well. Okay, so the sequence must be consistent. Okay, so what you write in H1 must be consistent with the calculation in step number 5. So if you follow the one in the slide here, you get negative 0.662. So again, it will be a 3-part answer. First, whether the value, the calculated T here, is inside or outside the area of rejection. Secondly, whether you reject or do not reject. And thirdly, the meaning of the conclusion. So you can see here clearly. So 0.662 negative is outside the area of rejection. So we do not reject. Okay, do not reject H0. So in the third part, because we do not reject. Okay, so again, go back to your H1. Okay, whenever you have finished your calculation and you want to write your H1, you want to write the conclusion in the third part of step number 5, always go back to your H1. So in our case here, we do not reject. So do not reject means we cannot support H1. So your conclusion for step number 3, okay, in step number 5, part number 3 just now, because we cannot reject, we conclude that the mean of Wallis is not equal to, there is no difference. Okay, there is no difference between the mean of Wallis and the mean of Atkins. Okay, so be careful, because the word difference is already a negative thing. There is not. Okay, you cannot use there is not equal. Okay, so there is no difference. Okay, so there is no difference between the mean of Wallis and the mean of Atkins. If you reject, means there is a difference lah. Okay, because H1 means the mean of W tak sama dengan the mean of Atkins. Okay, not equal to the mean of Atkins. But because we cannot reject, means we cannot say that there is a difference. If you reject, means there is a difference. Okay, so in part number 3, if in your conclusion, okay, because we cannot reject H0, so we conclude that there is no difference. Okay, there is no difference between the mean of W or Wallis and the mean time of Atkins. Okay, so that is using the pool t-test. Okay, so I think both. So first, what we have covered today, first we discussed on the Z test. Okay, when sigma is given. Okay, so under sigma is given, we are just using this simple formula. Okay, again, whether you are using Z or T test, okay, the main thing is how you construct your H1. Okay, so in the first example under Z, the keyword here is longer. Okay, so we use the sign bigger than. Okay, the right side, I mean longer or bigger than. Okay, but the second thing that you need to be particular is that the order of how it appears in your H1. Okay, because in this example, I think it's very clear. You want to test that standard time is longer than the U time. Okay, so it will be standard appear first. So because standard mu s appear first, followed by mu u. So in your calculation, it will be x bar s minus x bar u. So for a one tail test, whether longer or smaller than, I think it is quite clear. You need to follow what the question wants you to test. But for a two tail test, using the from the keyword, is there a difference? So this is something that you need, that there could be a difference in the approach between different students. So between, sorry, this is proportion. We haven't discussed proportion yet. Okay, so in this particular example, is there a difference? Okay, so the way you write your H1, the order which mean appear first, whether mean W or mean A appear first, that will also affect how you write down your answer in step number 5. Okay, so in this particular example, we choose to the slide put mu Wallis not equal to mu Atkins. So it will be mean of Wallis minus the mean of Atkins. Okay, and then you need to be consistent until you arrive at the conclusion. Okay, so I think that's it for today. So we will continue on next Thursday with the dependent and independent test. Okay, and hopefully maybe we can continue finishing up in the syllabus. Okay, depends on, I think if we finish earlier, then you have more time to do your assignments. Okay, so there's no point delaying or teaching slowly when we can finish some of the syllabus earlier, so that you can have more time maybe to do other assignments for other subjects as well. Okay, so we stop at this slide.